Hello, everybody. Welcome for the second day of the CC Grid 2020 and 2021 conference. So it's a joint event this year because we had 2 years in one session. So today for the live event, we will have two sessions. We will have a keynote from Professor Feng, and we will have a best paper session. You can see the program on the CC Grid 2021 website. So it's a very good honor to have today Professor Feng. He is professor from Virginia Polytechnic Institute and State University in USA, who is a very famous speaker and very famous researcher working on several subjects from energy efficiency to large-scale systems, data analytics, and also machine learning. So, Wu, it's a very great pleasure to have you today, and I give the microphone to you, and the floor is yours. You can share your screen and show your keynote speak. Thank you, Wu.
Okay, thank you, Laurent, and thank you to the CC Grid organizers for having me to give this talk. Let's see here. Just want to make sure.
So I remember to all the audience, if they want to ask a question to Wu during his keynote, please send your question through the chat, to the Zoom chat, and you send it to me or to any of the, send it to me. So I will ask the question to Wu after his keynote.
Okay. Is my display showing up okay?
For me, no, not yet for me. I don't see your display now. No.
So let me, I should double check and do this again here. And now I think it should work. Let's see.
Yes, it's beginning.
There we go.
Yes, we can see it.
Are you seeing
perfect.
The full screen?
Perfect. Okay. It's full screen. Yeah. Thanks.
Okay. Thank you. All righty. Let me just put this as the laser pointer too, so you can see. Okay. Thanks again to the organizers for having me to give this keynote talk, and thanks for attending wherever you are in the world, whether it be in the Western Hemisphere, Eastern Hemisphere, or what have you. Today, I'm going to talk to you about at the synergistic intersection of scalable computing, data analytics, and machine learning. And as Laurent noted, I am a professor at Virginia Tech. In the departments of computer science, electrical and computer engineering, biomedical engineering, and mechanics as well. And you'll see flavors of all of these disciplines in this talk. Alternatively, a more pithy and informal title to the talk is really compute faster and compute smarter. And so you'll see this throughout the talk about computing faster and computing smarter. So I'm going to talk a little bit about the new, or maybe it's not so new now, but the new landscape of computing. And this is something that was recently published in, I missed the citation here. This was published in the Communications of the ACM by Hennessy and Patterson in 2019, just a couple of years ago. And they pointed out that they plotted the growth of single core performance using the SPEC-int CPU benchmark. And processor clock speeds plateaued to 3 to 4 gigahertz by the mid-2000s due to the excessive heat being generated by higher clock speeds, and thus forcing the computing industry to embrace parallel computing. And initially, this is homogeneous parallel computing with multi-core CPUs. And they went to multi-core as a way to continue to improve microprocessor performance, given that the spec CPU int benchmark had plateaued. Coincidental to this plateauing of the CPU clock speed in the mid-2000s came the tracking of our digital universe of big data in the mid to late 2000s. And you can see that here, that while CPU single core performance started to plateau here, this is in the mid-2000s to the late 2000s. If we take a look at the digital universe, well, our digital universe was growing exponentially starting from the late 2000s with respect to this chart. It's grown exponentially from 1.2 zettabytes in 2008 to nearly 40 zettabytes in 2020. This indicates a doubling of data size every 2 years. So we've gone from this doubling, it used to be doubling every year and a half in terms of performance, to doubling every 3.5 years, to the gray is doubling every 6 years, to now the single-threaded performance is only doubling every 20 years. And in contrast, we see the flip, converse, if you will, happening with the exponential growth in data. So we have a problem, and that is the rate of growth of in big data is far outstripping the rate at which computing can brute force compute on this data. And so what I want you to take out of this is we not only need to compute faster, but we also need to compute smarter. And that forms the roadmap of the talk for today. I'm going to talk about how this new landscape of computing has evolved to enable us to compute faster, to improve the rate of computing, the challenges in this new faster landscape, and then I'll give you a broad vision of 21st century computing in light of where we're at architecturally and algorithmically. This will be at the synergistic intersection of parallel computing, data analytics, and machine learning. And what you're going to see as a bit of a foreshadowing is we're combining these aspects into high performance parallel and distributed computing systems as a way to scale our ability to solve problems in science, engineering, and other domains. So from that vision, I'll talk about some of the synergistic co-design that we're doing from the bottom up to support this vision. There's many components to the system that have all demonstrated promise in allowing us to not only compute faster and more efficiently in terms of how we map and optimize threads on all the different types of cores we have, but also to do so more smartly well, so it's a combination of both faster and smarter. So that's from the system perspective. And then as time permits, I have a couple of applications also that leverage the work that we had done at the synergistic intersection of parallel computing, data analytics, and machine learning, and how it applies to some of the applications. And I think that it's of most relevance in terms of timeliness. We have a project called Compute COVID-19 Plus I can get to. All right, so with that as a backdrop, again, this is about computing faster and computing smarter. Like I said, the problem is that the rate of growth in big data is far outstripping the rate at which computing can brute force compute on the data. And so what we'd like to do is see if we can increase the rate of computing, if not through the single-threaded performance, which you saw is not possible anymore, to leveraging parallel computing in some fashion to increase the rate, but then also leverage the computing to do our computing more smartly. So the architectural approach to this is to improve the rate of brute force computing via scalable parallel computing as well as heterogeneous computing. So that's nothing that's particularly new to you folks. Is we by the end of the 2000s and around the turn of the previous decade in 2010, we had this. This is meant to be a bit of a cartoon. This is like the Swiss Army knife, a mega Swiss Army knife. This is meant to be a metaphor for a CPU core. So we had 4 CPU cores, and each CPU core had so many different instructions and generality in terms of supporting general purpose computing that it could be viewed as a Swiss Army knife of computing. It could do everything okay, but nothing particularly well. And so for this particular Swiss Army knife CPU, say some of the microprocessors will have, the x86 microprocessors will have on upwards of 500 plus instructions associated with it. Since then, the idea is to instead create a set of specialized processors. That is, we want to customize some of the processors so that we have the appropriate tool or processor tool, if you will, for the right task at the right time. So you want to use the specific processor tool that is best suited for the task that you're running. So so that's a part of some a keynote talk that Professor Andrew Chen gave about the 10-10 paradigm replacing the 90-10 paradigm. And so this is the heterogeneous parallel computing aspects. And so we're seeing this in spades right now. Most recently, you see heterogeneous parallel computing in the small. So this is Apple's M1 SoC. And so let me back up a little bit. Heterogeneous parallel computing in the small, I'm thinking about like smaller scale parallel systems. And so this is Apple M1 system on a chip. And you can see before the Apple M1, we had multiple different processors here that have now since been consolidated onto a single chip. And each of these processors had their special purpose. And so even before this, rather than have a sea of homogeneous general purpose CPUs that can just do any given task relatively okay, and in some sense just have a tool chest of Swiss Army knives, like I showed on the previous slide. The idea is to have a tool chest of different types of processors that can deliver much better performance than a CPU on certain tasks at certain times. And so this was part of the start of it. This is beforehand. You could see that Apple had it as separate chips. There's the Intel CPU. Here's the AMD Radeon GPU. There's a Thunderbolt controller. Here's this is the Apple T2. This is a security chip. And now these CPUs, GPUs, the security chips are now all integrated into a single chip here. We also have a heterogeneous parallel computing in the large. More of you will be aware of the DOE Summit supercomputing node. This is one node out of 4,608 possible nodes. And and I should back up just a little bit. One of the things I wanted to note here is that with this integration, the number of parallel threads at your disposal is on the order of 25,000 parallel threads in this small heterogeneous parallel computing system on a chip. The numbers, this massive parallelism is even larger on the DOE Summit supercomputer. You can see here that there's 48 latency optimized cores, the IBM Power 9 CPU. There are 30,720 throughput oriented CUDA cores, and there are 3,840 high density tensor cores. In all, this node combined with 4,608 total nodes and lots of expertise in the hardware and the software of the supercomputing system was able to deliver 149 petaflops on the LINPACK benchmark. So our challenge is, how do we deal with the massive parallelism? How do we efficiently utilize these massively parallel resources? I just noted that there's on the order of 25,000 concurrent threads that are running, that can be run at the same time on this Apple M1 chip. And likewise, in the large, there's significant intra and internode parallelism on the DOE Summit supercomputer. There's 2.4 million cores in this system. Another challenge that we face is heterogeneity. This is not by no means an exhaustive list, but you can see here's the user over here to the left. Here's some different programming abstractions that kind of club together. I didn't say OpenMP and OpenACC, given their directive base, but these are the different programming abstractions. And so the user and their applications, they face a world of emerging parallel architectures that is very diverse with respect to its programming and its execution models, and they've complicated the design and development of high-performance computing applications, as end users over here have to decide which architecture or which processor over here, which programming language, which algorithm, which implementation technique is appropriate for or suitable for their applications. And so you've got this potpourri of different processor devices, and I think the top two I have are the Xilinx FPGA and Altera FPGA. This is an AMD GPU. This is now the discontinued Intel Mic or Xeon Phi. This is a AMD APU, which has a CPU and GPU fused together, and this is a NVIDIA GPU. You could also have the Intel and AMD CPUs here, which you can run OpenCL and OpenMP on as well. So it requires extensive hardware software expertise it's required to overcome this paradox of choice that you have. And achieving high performance and interoperability across these heterogeneous devices is tedious and error prone, even if you are an expert. And so okay, so that's for heterogeneity. And finally, with respect to scalability, there's this increasing gap between computation and communication, or perhaps I should say computation and data movement, whether the data movement be with respect to memory accesses or network communication. And you have this increasing gap both within a node as well as across nodes. And even worse is that this gap will increase with the number of nodes and processes because of contention on a shared network and contention on shared memory bandwidth. Okay. So the scalability of user applications is ultimately limited by the inherent data dependencies within and across these nodes that then cause communication to have to occur, as well as synchronization in many cases. So what we'd like to do is predict execution bottlenecks, because these are crucial for application mapping and optimization for performance. Right, so I've just laid out the set of challenges that we face in the computing new landscape of computing right now. And so I'm going to go to this roadmap and talk about my vision for the 21st century of computing at the synergistic intersection of parallel computing, data analytics, and machine learning. So the idea is we want to co-design. This is probably a heavily overused word, but it's co-design of architecture, software, and algorithms to more efficiently and intelligently compute on the data, and efficiently from a perspective of computing faster, and more intelligently with respect to computing smarter. And we did some of this work over a decade ago, where we would co-design the hardware and software together. And this is roughly, it was like 350 some fold speed up. And then when we looked at algorithmic refactoring for customizing it and towards a GPU, we ended up with a massive speed up. And so this is where many people in the heterogeneous computing have been able to experience, particularly for codes that are amenable to single instruction multiple data parallelism. So how are we going to do this co-design? We're looking to have some holistic design, compile, and runtime specialization of the software stack, from the low-level architecture all the way on up to the application. Again, at the intersection of scalable computing, data analytics, and machine learning. And we need this specialization of the software stack in order to bridge the semantic gap between the user applications up at the top, down to the system software, and down all the way to the hardware. And you'll see that on the next slide here. So in order to bridge, as I was just talking about, in order to bridge the semantic gap between the user applications here, the system software, and then the underlying hardware, what we'd like to do is capture some of the inherent application characteristics at multiple levels of computational granularity. We want to capture parallelism, the information flow with respect to the data dependencies, you know, a lot of this is captured through graph representations. In order to further bridge the semantic gap and adhere to these application characteristics across the multiple levels, we need to have cross-layer abstractions or models that we can rely on in terms of optimizing and computing smarter. And we want to drive towards automation frameworks for performance analysis, runtime adaptation, and interoperability between compute devices or compute nodes. Right now, even though there's heterogeneous computing within a node, we're homogeneous generally across nodes. So the DOE Summit supercomputer that I just talked about, it's heterogeneous inside. It's got a pair of IBM Power 9 CPUs, and it's got 6 NVIDIA Volta GPUs, but it's homogeneous across the nodes. All the other nodes are essentially replicas of it. There's certainly a case that could be made to have a set of different nodes that have FPGA acceleration, another different node that might have an AMD GPU, yet another one that might have some other type of device to speed up computing. So with this as the vision, what I'm going to do is spend a bit of time here and show you what we're doing with respect to computing, parallel computing, the analytic models, the data analytic models that we're doing just from a theoretical perspective, as well as leaning on machine learning as appropriate to enable these automated frameworks, and then in turn enable some user applications for the better performance and being able to compute faster as well as compute smarter. So let's take a look at this co-design from the bottom up. I'm going to look in particular at these 4 at a very high level. And so towards realizing our vision, so what I've done here is, let me back up just a little bit here. So I'm these light blue boxes is where I'm doing the drill down, and you can see that here in terms of the compile and runtime analysis. There's different components in here. I'm not going to be able to talk about all of them, but I'm going to give you a high-level overview of the various components, and then just spend some time on the ones that I think will be of more interest to the audience. I first start off with the granularity of computation here. So there's work that we're doing at the application, the kernel, and instruction levels in order to deliver scalable performance, both at the node level and at the cluster level. And so we have tools like AutoMatch, which is here for compile and runtime analysis. It generates a graph-structured program representation at the instruction level in order to estimate the execution costs of serial codes across heterogeneous high-performance computing architectures. So it's not, what we're doing is we're estimating the costs from a serial perspective and then generalizing it and looking at it optimally in terms of seeing how it would parallelize. So think of it as loosely speaking, for those that are aware of the roofline model from Berkeley, we're constructing a model that will estimate that cost of taking that code and then parallelizing it up towards the roofline of performance. So that's AutoMatch. There's well, actually, you know what I should do is so AutoMatch and COM Analyzer are at the granularity of instructions, whereas cores are it's a task size adaptive runtime. It's being the czar of the core. It's a play on words there. This works on threads, thread level, not instruction level, as is the adaptive task aggregation work and this metamorph work, which allows interoperable communication between AMD CPUs, AMD GPUs, NVIDIA GPUs. You could have them all intermixed, then you'd be able to run a parallel program, which right now in virtually all places you cannot do so. All right, so I'll just I dove in with AutoMatch, but let me go through each one of these. So there's IteraML, which is iterative machine learning. It's an automated optimization of GPU configuration, and you're going to see why that's so important. You can take the same program, same GPU program, and if you configure it slightly differently, you can get upwards of a 30 to 40% degradation in performance. And so we suffered through this and realized that there's got to be a better way of doing this. And so we realized the machine learning approach towards optimizing this GPU configuration that gets us within a few percent of optimal. There's something called Ensemble ML. This is this is an ensemble machine learning method for automated power and performance prediction for the GPU. AutoMatch, which is automated estimation of execution costs of a code on a myriad of different devices. And the idea is that if you have 5 different devices and you run AutoMatch on these 5 different devices with a particular workload, AutoMatch will predict the relative ranking of best to worst in terms of the devices that you have available to you. And that's a within node thing. COM Analyzer's automated estimation of communication costs, and that's across nodes. So AutoMatch is within node, COM Analyzer is between nodes. We have Corzar, which simultaneously uses CPU and GPU at the same time. So the idea is that most of us, when we write the GPU accelerated programs, we tend to write it where we're running along the CPU, and then we see something that we can be accelerated, like an FFT, a fast Fourier transform. We say, oh wait, let's make a call out to the GPU, and then the GPU has control in its silicon brain, and then when it's done with FFT, it returns control back to the CPU. And so this kind of ping-ponging behavior between the CPU and GPU thread of execution is very common in programs. And what Corzar does is like, well, if I have, like I've been gesticulating with my hands here, but if physiologically I have a left brain and a right brain, and I don't ping pong between the two, I'm making use of both my left brain and right brain simultaneously. It's just that with different levels of frequency, if you will, or different levels of workload. And so the same thing goes for Quasar. The idea is like, why should one or the other processor be lying idle while the other one is actually doing work? Why not make use of both brains at the same time, like we do physiologically? And then finally, there's adaptive task aggregation. It's a way to do more efficient dependency management so that you can execute sparse or regular computations much faster. And finally, interoperably simultaneous execution and workload distribution on a truly heterogeneous cluster. So these are a subset of the components that we are looking to realize as part of this larger system. And what I'm going to say is I'm going to cherry pick here a bit, and I'll talk about ITER-ML, AutoMatch. These two are compile and runtime analysis tools that do prediction and projection and allow you to set up your in ITER-ML, it allows you to set up your configuration for better performance. AutoMatch allows you to figure out of the heterogeneous devices you have available to you, which device would be best suited for executing a particular code on. And in addition, it could be used, like if I had 5 different devices, it could be used to decide how much work to give to each of the 5 different devices from the perspective of their parallel computing capability that AutoMatch projects based on the workload and the code, the workload that is provided and the underlying devices that it's going to run on. All right, so let's see here. So here's, I'll talk about iterative machine learning. So here's one of the bigger problems. There are many configuration parameters for users to tune to achieve best performance. Many of you might just write your GPU code and follow the guidelines in the CUDA programming guide or OpenACC programming guide or what have you. But it turns out that there's a lot of parameters that may be just set for you or by default. And things from thread block size, number of streams, the resource register usage, compiler optimization flags, and so on. It turns out you'll have on the order of millions of potential software configurations for the same code. And so what I'm going to show you here is the thread block size, just looking at the thread block size, which is one of many, many, many different configuration parameters you could look at. And I'm going to show you something called a lid-driven cavity code. It's a canonical code in computational fluid dynamics. And I'm going to show you it with respect to varying GPU thread block size. I have the initial results that are from fairly a few years back was on the NVIDIA Kepler KM20M GPU. And it's been updated to the NVIDIA V100 GPU as well. And I'll show those a little bit of those results as well. So here's what we did was when we ran the lid-driven cavity code, when we compiled it, it defaulted to a 64 threads along the X dimension and 4 threads along the Y dimension when we compiled it. And based on this heat map, what you see is that you see that's fairly light blue. This light blue corresponds to 79 gigaflops. And this one in particular was on the K20M. The challenge here is that we have a huge design space, even when considering only one parameter, that is thread block size. What should I set my thread block size to? Well, you can do a brute force search. There's 7,262 runs. It'll take you more than a day to search on in this case, the Kepler K20M. And so this is the brute force search. It's truncated just so that it could fit on the slide. Yeah, so the default, as I said before, was 79 gigaflops. And look here, the optimal is over here. And in fact, what I ought to do is maybe I can take a pen to this so you can see it. Just oops. This is the optimal setting. It's an 8x8 thread block size. And what you see is if you look around that thread block size, you can see that you have performance cliffs. So let me, if you look around it, you see there's light blue and there's a yellow there. So light blue, yellows, you have a performance cliff around this highest optimal performance point. So, application writer can spend over a day to figure it out. You could then rely on developer experience. In this particular case, since 8x8 was the optimal, the recommended block sizes from the user guides are 64 to 256 threads. And so here are the examples. And so it turns out in this particular case, it works out. It won't always work out to be that way. That's just what this example shows. Let's see. So here it is, 8x8 or 64 threads was the ideal case. But the best parameter setup will vary even between applications. So what you see here is that, so we took the common sizes, 8x8, 8x16, 16x8, and 16x16 here. Let's see, laser pointer. So these are the ones that are common and recommended based on user experience. And you can see that none of the thread block sizes, these common ones, end up producing the ideal performance. So we ended up doing exhaustive search for all of these different benchmarks. And we normalized the best performance to 1. The lid-driven cavity code, the ideal size was not 8x8, but instead, whoops, I jumped ahead. But instead it was 4x32. And then furthermore, if you take a look at, oh yeah, so this is the ideal size 4x32 when running on the V100 GPU. So what you see here, interestingly enough, is that what used to be optimal points along this hyperbola, the top end of the hyperbola, is not so optimal now. It's in the green, and that the scatter of better performance points are down in this hyperbola area. So there's differences in terms of what the best parameter setup is between applications as well as between different devices. So so that's the issue with relying on end user experience. It's going to vary between what the best parameter is. It's going to vary between applications. It's going to vary between the devices. So you could take a look at statistical methods. You could pre-train a model in a certain system for a certain system, and then when a new application comes in, you profile it and then predict the best setup using the profile data and apply it. And so the issue here is that to build the model, a priori, you need a very large training set, and it may, and then you predict the best parameters based on the real-time profiling data model, but it may end up performing poorly for new algorithms on new devices or systems, just like here on new devices and new systems. You could also do reinforcement learning methods. It doesn't require any prior knowledge of the target system. You just run it continuously to adapt and dynamically update parameters. The problem ends up being that it'll take the decision system significant time to converge to what would be the optimal thread block size. So our challenge is how to deploy new applications, algorithm systems, and hardware accelerators, and tune the multidimensional search space of hardware, software, and algorithmic parameters to optimize the applications. And I've only just shown you just with the thread block size. So we're doing this with no prior knowledge and no pre-trained model, unlike the deep learning approaches, to deliver near optimal performance with the least amount of effort and domain knowledge. And I'm not going to get into the details other than to say that it's a fairly simple, straightforward approach. Instead of just applying a non-iterative machine learning technique, what we do is we take the machine learning technique and the sampling that is done, and we simply break the samples into the expected samples into smaller bins, and we use the samples from one iteration to then guide us into potentially better samples for subsequent iterations. And so what ends up happening is that we show let me just say that what ends up happening is when we apply the iterative machine learning, we end up finding a point that is within a few percent of the optimal performance. And it's maybe somewhat surprisingly to some people is that it's not a power of 2. It's the block dimension is 24 by 21, and it produced nearly 101 gigaflops of performance. So with ITER-ML in place, that's with respect to our heterogeneous computing aspects, and using machine learning with data analytics, and in order to configure the parallel device, in this case the GPU, to get us better performance. You can get as much as a 30% difference in performance simply by tuning this thread block size. Next, I'm going to talk about auto match. And with auto match, the goal is automated analysis of serial code, or you can think of it as a MPI rank. You could to construct a cost function of its optimized parallel execution on heterogeneous processors. This ultimately ends up enabling, I should say, efficient workload distribution that automatically achieves nearly the same performance as having a profiling-driven oracle. So AutoMatch takes the various bottlenecks in a computing subsystem, finds the parallel performance upper bounds. So you think of this a little bit like the roofline model, and then creates a ranking and relative execution cost of the different processors that you are considering to run your code on. So this is helpful for application scientists who want to figure out, oh, well, I have this kind of code and I need to run it a lot. Which kind of device should I get? Should I get an AMD GPU? Should I get an NVIDIA GPU? Should I get the new Intel GPU, or what? So this gives you a quantitative perspective in terms of what would be best to run the code on. So the user can then, the user basically takes his algorithm, or his or her algorithm, and then has a bunch of architectures, heterogeneous processors that they're selecting, and from AutoMatch will come back a rank of the different devices. Let me just move on in the interest of time here. Whoops. So AutoMatch is a automated framework for relative performance estimation and workload distribution, as I just said. So it consists of compiler-based application analysis. So it has an as soon as possible schedule for the target application on a theoretical architecture consisting of infinite resources. So is how we create the model. We have dependency analysis. That's a standard static def use chains to track data dependencies through registers. We have dynamic points to analysis to track data dependencies through memory operations. We also look at considering the vectorization potential in conjunction with the instruction mix. examination of the data locality. So we perform dynamic reuse distance analysis to estimate the upper bound on the data locality, as well as looking at global synchronization so that we can also then dynamically detect loop carried memory dependencies. Then ultimately, the number of global synchronization points is the trip counts of the inherently sequential loops or serial loops within interparallel loops. There's also the abstract hardware modeling. Initially, when we did this work, we were taking the data directly from the spec sheets, but that ended up causing enough noise in the analysis. It introduced noise into the analysis that what we had to do instead is resort to creating an abstract hardware model by doing micro benchmarking to instantiate an abstract hardware model for each architecture that we were targeting. So we looked at floating point throughput, memory bandwidth, memory access latency, and synchronization. And then next, there's the analytical models. They're just first order performance models of computation, memory, and synchronization time that can be generalized for different types of architectures. And that's what ends up leading us to understanding the different bottlenecks, the parallel performance upper bounds, and thus producing the ranking and relative execution costs for each of the devices. So I'll just take a FFT and I'll run it on 5, 6, 7, however many devices that I want, and AutoMatch will spit out a ranking of which device is will deliver the best parallel performance. Yes, I already just said that. Here's just some results. Lower is better here. So the Mini Ghost app is a mini app for exploring boundary exchange strategies using stencil computations in scientific parallel computing. Heat 2D is a heat transfer simulation in two-dimensional space, and SPMB is, of course, a sparse matrix vector multiply. So what you can see here is that lower is better. So because execution time is normalized. Actually, this one is not normalized. Sorry about that. This is the execution time. You can see that the default setup is what's shown in the dark black, and again, lower is better. So the default setup in all cases produced the worst performance. The far right one is the profiling oracle, so profiling driven oracle. So you can see that in all the cases, well, most of these cases here for Mini Ghost, our AutoMatch produces the same execution time. It predicts the same execution time, relative execution time on across all these grid sizes. And it's pretty close here as well. You can see all the two right-hand-most bars are all relatively close with one another. We don't do quite as well as some of the sparse matrix vector multiplies here for the few that are in here. So what the summary is that this enables efficient workload distribution that automatically achieves nearly the same performance as the profiling-driven oracle. And so the results, the accurate prediction of the relative ranking and performance of the different devices, and characterizing the gap between the achieved parallel performance and the performance upper bounds. This ended up allowing us to pinpoint that several of the open source benchmarks are not equally optimized for each architecture type. So there's already a bias when you start to evaluate the goodness of your system software or what have you, and you're using a benchmark suite that is potentially biased for one architecture type versus another architecture type. All right, so let's see here. I will talk briefly about some runtime adaptation with respect to Corsair, and I'll skip over the aggregate adaptive task aggregation in the interest of time. So Corsair, you want to automatically spread or schedule tasks across heterogeneous computing resources. So unlike the paradigm that is common today, where you're running on the CPU as, if you will, the master, and then you look to offload work to a GPU or an FPGA or DSP or what have you. The idea here is that you're ping-ponging between the CPU and the accelerator device and back. And so the idea here is we want to run across all of the available resources automatically or as appropriate. And so we want a runtime system that intelligently uses what's available resource-wise and optimize for performance portability, and not have the user have to do this or implement this for themselves. So we look at the applications that's, say, written with CPU and GPU directives like OpenMP and OpenACC. And all we're doing here is we're shimming in a layer. We are not proposing to replace any of the existing software stack, but rather complement and add a piece that as a new layer between the OpenMP accelerator directives and the existing CPU and GPU schedulers. So yeah, so the way we've done it is we've just done it as an extension to an accelerated OpenMP syntax for programmability, and it automatically divides parallel tasks across arbitrary heterogeneous compute resources for functional portability. Right? So this is what it looks like. Here's traditional OpenMP. Here is OpenMP with accelerator directives. So you have accelerator region loop, accelerator copy in, accelerator copy out, accelerator copy. And this is our proposed extension. It's identical to the OpenMP up here, except that it just adds another clause as to whether or not you're going to do a ping pong scheduling of computation between the CPU and the accelerator device, or you're going to do a simultaneous scheduling of both devices. Okay. So it's only an adding of one line, and then the splitting and the assembly are all automatic. So here you see it's hetero 1, dynamic. Versus if you wanted to do this yourself manually, this is the kind of code that you would have to end up writing yourself to run the cores in parallel. So let's see. So this is the traditional behavior of OpenMP accelerator. Here you have parallelization on the CPU, then you have a barrier, and then you do parallelization on accelerator, and then you have a barrier. And instead, what you'd like to do is run the CPU and the GPU at the same time. And you'd like it so that if this is time going from left to right, you want to minimize the slack time between when the GPU completes its execution and when the CPU completes its execution, in order to not leave resources idle and waiting. So longer term, you could start to see, all right, well, maybe I have 4 GPUs and a CPU that I want to run across. So there's a number of different application types that I'm not going to get into. There's this, I'll just say that there's a single pass region, one with few passes, one with many passes. And then you can also think about what's suitable for the GPU and what's not suitable. So the GPU, if you give it a set of tasks and it takes this long to do, and the CPU can get it done this quickly, you want to make sure to move the work that's here to the CPU, as more of it to the CPU, so that there's a better balance in execution time. And so there's a linear programming formulation for this that I'm not going to get into the details for. It's just to say that this is a problem that's solved at the beginning of a pass or a manufactured sub-region that we look at. And then at the end of the pass, this linear programming model is solved to minimize the slack time between when a GPU ends its execution and the CPU ends its execution. So we tested this over some benchmarks. This is NAS conjugate gradient benchmark. There's GEM, which is it's a molecular modeling, electrostatic modeling benchmark, there's k-means, and then Helmholtz. And it turns out that the Helmholtz, the way that this was written as a Jacobi iterative method, is highly GPU unsuitable. What you see here is this is automated. This is all based on data analytics, a data analytic model, and a linear programming formulation and solving. We do not have any machine learning in here, but the problem that we have and that we're looking to apply machine learning is in the case of Helmholtz. What ends up happening here is when we used these co-scheduled schedulers, meaning the yellow and the greens and the blues, these are using both the CPU and the GPU at the same time. You can see that the performance actually drops off from what just running it on a CPU. And that's because the way we have the initial ratio of CPU and GPU work, loosely 1:4 ratio, it takes the runtime system some time to figure out that 4 times more work on the GPU, all of it needs to be moved over to the CPU. And that's the overhead involved in figuring that out. But for the other codes, you can see that when running just on the CPU or the GPU only, in general, when we do the CPU and GPU together, we end up with much better performance. In some cases, the performance is almost twofold better. In the case of k-means, it's twofold better than the CPU.
So it could be nice to conclude now in order to have time for questions.
Sure. So what I'm going to do is I'm just going to jump to here. Let's see. I was going to spend just a few minutes talking about our compute COVID-19 project for what we were doing in terms of combining machine learning data analytics and high performance computing. So I'm just scanning through these really quickly and just jumping to the punchline here is that so far compute COVID-19 plus work. In contrast to the RT-PCR approach, which only generates an accuracy of as little as 62% due to the human in the loop handling, we're able to do COVID-19 detection to the point of getting 91% accuracy, which is 30-some% better than the traditional RT PCR test that we are getting today. And so this is something that we could have in hospitals, and the turnaround time, instead of being on the order of hours to many, many days, the turnaround time for the inference of this is measured in seconds here. Okay, so that's it to conclude. The vision for 21st century computing is co-design of architecture, software, and algorithms to more efficiently and intelligently compute on the data, computing faster, computing smarter. And I gave you some teasers in terms of what we've been doing with respect to creating a holistic design, compile, and runtime specialization of the software stack to tackle this big data and big compute problem with artificial intelligence. So that's all, folks.
Thanks a lot, Wu, for this wonderful keynote where you show the complexity of developing application on these big machines and multi-cores architecture. Thanks a lot. So we received quite a lot of questions, so I will go quickly through some of them in chronological order. So we have a question from Carlos about the impact of the thread block size when you show your results on GPU. How the thread block size and why this block size affects the performance? Why do you have cliffs? And also the performance appear to be very symmetric on some axes, so you could halve maybe the search space.
Yes, so that's excellent questions. I was gonna just return to these.
Oh, Carlos, I see you are here. You can have it. Ask it lively. Okay.
Yeah. So maybe I should go back further.
Yeah, this one.
This might be useful. So because I don't work at NVIDIA, I don't know how the underlying thread mapping is, and I don't know how the scheduling is done. That we could potentially look at a project and try to do tomography on the GPU, so to speak, and try to take measurements from the outside to try and infer what's going on in the inside. But what we found surprising, so the short answer to why are there performance clips, I don't know. But what I do know is that we were able to use machine learning, and we knew that we were likely not going to be able to find these optimal points because it's in the sea of bad performing points. But we were pretty confident that we were going to be able to find something here, which we did. And I showed you here with respect to the V100 GPU. Yeah, it looks somewhat symmetrical, but I mean, you can see up here, they're good red points here, but they're non-existent over on the flip side here. They go to green. And then there's still other applications. I don't have them in this slide deck, but like there's like odd banding, like horizontal banding and vertical banding of the best performance, and it's based on the application. It's based on the interactions with the system software, and then it's mapping to the underlying architecture. And so they're all influencing one another in some way that I just don't know, you know, from a analytical perspective. And what we're doing right now is we're simply applying machine learning to get us to that better performance right now.
It's not easy on GPU. Okay, thank you. I think Carlos agrees. I see on the web. Okay, so you have a question from Apan. So do you think in the future that machine learning driven predictive modeling will completely replace compiler and runtime heuristics? Or do you think there are fundamental limitations that will require human intervention?
Oh, wow, that's a really good question. That's a loaded question.
Do you still require some human expertise? Or
so, I mean, the holy grail is this magic parallelizing compiler, right? All the way back to the 70s and 80s with these parallelizing Fortran compilers, which were easier to parallelize just because you didn't have the notion of pointers and alias. Well, you did have aliasing, but you didn't have pointer aliasing to the degree that we have now. So I look at the machine learning and even deep learning that we're going to be applying to the problem with respect to the Corzar problem, the scheduling problem, as being complements to the analytic, the more rigorous analytic methods. So for us, with respect to say Corzar, well, I guess I should. With respect to Corzar, we have an exact theoretical model that helps us decide how to go about distributing the work across the CPU and GPU. Where machine learning would help as an extra gate or an extra query, if you will, is that based on what we get from the linear programming optimization, we can then potentially do like a machine learning test check to decide, all right, well, we should maybe be shifting things more, or based on what has happened in the past. So one of the problems with our linear programming formulation is that we are dependent on what has happened in that same region in the previous iteration of it. And so we're tracking based on the history, but we have some codes where we make a decision based on the most recent, we make a decision here in the most recent history, but then it flips it to the wrong side, flips it to the wrong processor. And then when we flip it to the wrong processor, then when we try to do it back on the past region, we're directly 180 degrees out of phase. So one of the benchmarks, we kept predicting the wrong thing, and I'd say a deep learning model that we could do some inference on would help us get out of that that I guess you would call it a global minima, the really poor performance, because we're ping-ponging directly out of phase from the regions that are executing.
Okay, thanks, Wu. Apan, you are okay with this answer? Yes, okay, thank you. So we have a question from Muhammad Zakaria. So Muhammad says that applications and workloads performance may vary significantly due to other factors such as resource contention. Yeah. So predicting applications performance on certain hardware is quite tedious and will take considerable time in such application-specific decisions. How the scheduler will handle this situation?
Great question. I love these questions. It's good. It's a little, I feel like it's a little late for these questions here.
Yes.
but no, this is a really, really good question. So one of the things that I did not mention, so like with auto match, if I were to go back to auto match, what I didn't mention with respect to auto match was just this is the auto match framework here. It turns out that even for these arguably simpler mini apps or proxy apps, that when we put it through our LLVM system, this process takes on the order of hours to compile the mini app and to get us the information that we need. So this is something that we would be doing more at compile time offline. In terms of the question, in terms of things at runtime, if a good enough deep learning model can be generated to make adaptive decisions to help complement what you look at, say, like when I suggested the linear programming formulation for the adaptive runtime scheduling. If a good enough deep learning model is in place, you can make the decisions fairly quickly. And what I would say is, I'm going to jump to, let me show you performance. So this is one where we're working on a deep learning model, and we're trying to infer whether or not the person has COVID-19 or not, and we're able to do it based on the regular images. It's 86%, and when we put it through our enhancement AI convolution deconvolution network, there's 37 different layers, and then put it through our analysis AI, we can get 91% accuracy. And when we do this inference at runtime, it's only taking on the order of 1 second. Now, this is different from the configuration, because all the interactions, like you said, between the application, between the system software, between the underlying hardware. I think that it's going to be difficult, but what we're doing is you could kind of see it based on the vision. We've been chipping away at the problem and carving off pieces of it to try and tackle and address. And so one of the next pieces is, like in Corzar, is to identify through deep learning and the profiling from the deep learning how to set the ratios initially so that you don't have a adverse performance impact on applications.
Okay, thanks, Wu. So two last questions, so maybe a quick answer.
Okay.
A question from Yuk Wong. Does your model and solution work on the latest GPU with Tensor Core, such as A100 or RTX 3090?
The short answer is yes. For the CUDA cores, which is what I showed, the V100, which is inside. Well, I don't know if you say the the latest NVIDIA. It should work. We haven't tested it. The latest one that I've tested it on has been the NVIDIA Volta, which is the latest one that's inside the NVIDIA, not the NVIDIA, the Oak Ridge National Laboratory Summit supercomputer. But I don't see why there's any reason why it wouldn't work on the newer GPUs. We actually have been running it on the K20, the P100, the V100, and we've gotten very different results for the same application that's running.
Okay, very clear. Thanks. One question from Rashmi. Do you have any data repositories related to this research? I think Rashmi wants a web link, maybe. Or...
Oh, sure. I can. I would say that well, data repository. I don't have the data. We have some GitHub repositories.
Okay.
I have, but like in terms of the details of the technique and like I can. It's actually in the. You can see it was in the bottom left of my slides. It's synergy.cs.vt.edu.
Okay.
You can go there and you can find a lot of material. And then, so let me see here. I don't know if this,
I think it's
if
enough.
the chat works.
No, I think it's enough. Okay, perfect.
Okay.
So maybe one last question from me. You mentioned in your last slide that you propose to compute faster, but also to compute smarter. So do you include other metrics than classical performance like speed up, execution time, but do you also include metrics like energy efficiency, resource usage, and so on in your stack?
Yes, another very good question. That is, it was unfortunately, that was one of the pieces that I decided to skip over.
Okay.
In this particular side, you could see that, let's see here, let me show that. You can see that, whoops. Yeah, so Ensemble ML is automated power and performance prediction for the GPU.
Okay.
So it uses an ensemble technique, and some of these other techniques can be generalized to consider power as well. Cores in particular, we were talking about considering power. What's more difficult though is optimizing and considering performance power at the same time. Usually you can optimize for one and under the constraint of the other, and vice versa, but not at the same time. It's a much more difficult problem.
Thank you. I think we will stop here. Thank you for this excellent Keynote presentation. I think everybody can upload virtually, at least from home. It was very nice. It was very nice to hear you. Yes, we see some of them applying. Okay, I'm closing.
Thank you very much.
Thanks a lot, Wu. And I wish you a good night. I think you are now going on your night in US.
Yes,
so
it's only 1:15 a.m. It's still early.
Okay. It's still early. This is perfect. Thanks a lot, and hope to see you in the near future.
Thank you, everybody.
Thanks a lot. Thanks, Wu. So now.